Hello and welcome to the videos for section 8.2. There will be 4 videos for this section. This is the first of the 4 videos. In this section, we will be looking at polar graphs. So in section 8.1, we looked at the polar equations, what the r's, what the thetas were referenced to. So remember, the rectangular coordinate system has our x-axis and our y-axis. We have the different units horizontally for positive numbers, negatives, and vertically positive numbers, negative numbers. The polar graph looks more like a wheel, and the bicycle wheel with spokes. So we're only looking at the right portion, the positive values, 1, 2, 3, etc. And then each of the lines we're going to draw here represent the different radian marks. So pi over 6, pi over 4, pi over 3, etc. So the values that we're used to on the unit circle, those just get transferred over and creates these spokes on the graph. And so no matter which radian measure we're at, we can be various units away. If we're talking full units, it could be 1 unit, 2 units, 3 units, etc. 4, 5, 6, however far out we want to go. So this is what the graph of a polar grid looks like. So the equation R equals A is a circle of radius, absolute value of A, centered at the origin. So for example, in the past, our equation for a circle would have been like x squared plus y squared equals 9. So that told us that it's a circle centered at the origin, and then the radius is the square root of 9, or equal to 3. If instead, if I wanted to graph the equation r equals 3, well, by definition, what is this telling me? It tells me that the radius is equal to 3. So no matter what radian measure I'm at 0, my radius is 3. At pi over 6, my radius is 3. At pi over 4, the radius is 3. And it basically gives you a circle centered at the origin of radius 3. Much easier to write r equals 3 and use the polar graph as opposed to the equation x squared plus y squared is equal to 9. All right, let's look at another example. So let's say we want to sketch theta equals pi over 3, and going back to section 8.1, we want to express this in rectangular coordinates. So let's look at the equation we're given. Theta is equal to 3. So that tells me what? I'm not given any information about the radius. It just says that when I am on the radian measure of theta is equal to pi over 3, that's this guy here, right? Because we have pi over 6, pi over 4, and this one pi over 3. So if r is 1, pi over 3. If r is 5, pi over 3. If r is negative 3, pi over 3. So it's this entire blue line. If I'm not given a value for r, it's just the radian measure itself, that line that's created. As far as the second point, theta is equal to pi over 3. So recall from our equation that tangent of theta is equal to y over x. So in this case, my theta is pi over 3. So that means I want tangent of pi over 3 is equal to y over x. And tangent of 3 is equal to what? Well, this is equal to square root of 3 over 3. So that means square root of 3 over 3 is equal to y over x. If I want to get y by itself, I need to multiply both sides by x. And that gives me that y is equal to square root of 3 over 3 times x. And that's what? That's this blue line here. So if x is 1, y is square root of 3 over 3. If x is negative 1, y is negative square root of 3 over 3. And it again would reproduce this blue line drawn at that angle. So that's two possible problems from this one example. Draw theta, convert it back to rectangular coordinates. All right, let's look at a little more complicated example. So let's say we're given the following. Let's say we want to sketch r is equal to 2 sine of theta. When we first learned how to do graphing, what was the methodology? We plotted points. I'm going to show you some shortcuts of how to remember what some of these different graphs look like that we're going to do. But if all else fails, if you are given an exam, exam 2, exam 3, the final exam, and you're told to sketch some equation, maybe you don't remember the general forms of some of the cardioids and the limacons we're going to look at, and you're not sure what this should look like, no problem. All you need to do, just like you did in the past, is plot points. So let's create a table. So I'm going to make theta and r. And what's the first theta we know? Well, that's when theta is equal to 0. We're just going to pick our different radian measures on the unit circle. When theta is 0, if I plug that in here, sine of 0 is what? It's 0, so 2 times 0 is 0. What's my next radian measure? Pi over 6. If I plug pi over 6 in for theta, sine of pi over 6 is 1/2. 2 times 1/2 is 1. Pi over 4, that's square root of 2 over 2, times 2 is square root of 2. I can keep doing this. If I have pi over 3, I get square root of 3. If I get pi over 2, I get 2, and so forth. 2 pi over 3, square root of 3. So you can see the numbers went from 0 up to 2 and then are coming back down. So if I try to graph this, so I'm going to draw my polar graph with a bunch of circles. 0, 1, 2. The highest value I get is 2, so I really don't need to make more rings than 2. So when my radian measure, my theta is 0, my radius is 0. So that means when I'm along the x-axis, I go out 0 units, which is right here. Now the thetas that I've chosen are pi over 6, pi over 4, pi over 3, and then 2 pi over 3. And again, if we kept building the table, we could go all the way around. So when my theta is pi over 6, the distance I'm away from the origin is 1 unit. So actually, let me use a different color so it's easier to see. So we had the origin point, and now we're 1 unit away. At pi over 4, my radius is square root of 2. Square root of 2 is about 1.414, so about 1.5. So it only has to be close, so we'll put it there. At pi over 3, it's square root of 3, which is about 1.7. So about 1 3/4 maybe, so about there. At pi over 2, it's 2. So out here. So what's happening here? What can you see forming? It's an arc coming around, and now that we start coming back, I'm going to get these points here, and if I connect the dots, it gives me what should look like a circle if my graph was drawn a little bit more to scale there. So you can see from the red that the graph of 2 sine of theta is a circle of radius 2. And that's not a coincidence. So in general, and again, this will be one of the cheat sheet items you want, if we have an equation, r is equal to 2 times a sine of theta, this is a circle with radius, absolute value of a, and the center is at a and then pi over 2. So in this case, this was like 2 times 1 times sine of theta. So our a in this case is 1. So it has radius equal to 1, and it has center at 1 pi over 2. So that's 1 unit away along pi over 2, and so the distance out from all these points has radius of 1. We can also have the equation r is equal to 2a cosine of theta. And this is a circle with radius a, so that's the same. But the center is at the point a and 0. So instead of shifting upward on the axis to pi over 2, we're actually going to move right or left depending on what our value of a is. So that's it for video 1. Again, these are going to be 4 videos. They're short. Each one's going to look at the different types of graphs that we are going to encounter. The first one was the circle, general form, 2a sine of theta, 2a cosine of theta. And then we have this circle. The radius is always the same, the absolute value of a, and the center just differs depending on whether it's sine or cosine. So come on back and we'll look at the cardioid graphs.